So question 11, we've got this reaction. This is the enthalpy change, and it wants to know which of these statements is true. So first of all, is less energy released on bond making than is taken in during bond breaking. So remember that whenever you have a reaction like this, you have to break the bonds on the left, and bond breaking is endothermic, so that will indeed take in energy. So that's going to give you a positive contribution. When you form the bonds on the right hand side, bond formation is exothermic, it gives out energy, and therefore that will give you a negative contribution. So if A were true, if it were true that less energy is released on bond making, it would mean that this positive term would outweigh that negative one. More energy would be taken in here than would be given out here, so you'd end up with an overall positive number, but you don't. You end up with a negative number. That means more energy is given out from forming the new bonds than from breaking the old ones, so A is not correct. Is the enthalpy change for the reverse equation plus 184.6 kilojoules per mole? Well, yeah, because that's the point. If you do a reaction in reverse, all that happens is the sign of the enthalpy change reverses, so it will be plus 184.6 kilojoules per mole. So B is the correct answer. If we just look at the other two just to see why they're wrong, enthalpy change of formation of HCl. Remember, formation of HCl means formation of 1 mole of HCl. In this equation, 2 moles are formed. So if only 1 mole was formed, delta H would only be half as big, because there would only be half as many bonds formed and so on. So it would not be that number. So that's why that's not right. And the temperature decreases during the reaction. Well, no, it doesn't, because it's an exothermic reaction, so the temperature will increase. So B was the right answer for that one. So question 12 is just reminding you about this very important issue of why reactions get quicker at higher temperature. The Boltzmann distribution gives you the insight into that. The first issue when you go to higher temperature is that the average energy of the molecules, the average kinetic energy of the molecules increases, and you can see that just in the position of where the maximum is. Okay, so you've got a maximum here at low temperature, but it shifts to there at higher temperature. So on average the molecules have more kinetic energy, which means they move faster, and that means they will collide more often. So that will make the reaction faster, but it's not the answer, because actually that's quite a modest effect in general compared to the other factor. So although it's a contributory factor, it's not the main one. The main one comes from the fact that you have this activation energy here, and it's only molecules that have an energy greater than the activation energy that can react when they collide. And at low temperature there's only that tiny population of molecules represented by that area there which have enough energy, but at the higher temperature there's this much bigger population, and that's the main reason it gets faster, and that's what it's saying in part C, that more molecules at the high temperature have an energy greater than the activation energy. That means that they will have a higher probability of reacting when they collide, so they'll get more frequent successful collisions. So C was the answer. The easiest way to think about question 13 is to think about enthalpy profile diagrams again. So here we've got a reversible reaction, and remember that you can mark on both the forward and the backward activation energies like that, because they both end up at the top of the same hill, and they just start either from the reactants on the left hand side for the forward one, or from the stuff on the right hand side for the backward one. So that's your diagram, and then remember that what a catalyst does is to provide a new reaction pathway where the activation energy is lower. And on this diagram it's very obvious that if you do that, so here's your new one with the catalyst, it's very obvious that the forward activation energy is now lower because there's a lower hill from there to there, but the backward activation energy is also lower. So if we mark those on, we can sort of show that explicitly. So if we just carry on across there, we can say, right, so there's the new activation energy in the presence of the catalyst, and that's obviously lower than it was without the catalyst. And here's the new one for the reverse reaction. So again, ending up at the top of the new lower hill and still starting from here. So this is the backward activation energy in the presence of the catalyst, and obviously that's also lower than this one. And of course what you also know is that the higher the activation energy, the lower the probability that a collision will be successful, and therefore the slower the reaction will be. So qualitatively you can see that both the forward rate is going to increase because there's a lower forward activation energy, but also the backward rate is going to increase because there's a lower backward activation energy. What you can't work out from the diagram, but what turns out to be true when you go through it mathematically, is that those effects are exactly the same in terms of the factor that you change the rate by. Okay, so the forward rate increases by the same factor as the backward rate, and the consequence of that is that the position of equilibrium stays the same. Okay, so that's the sort of background to the question, and the answer is therefore B, that both rates increase by the same factor. Okay, so if we think about an ethene molecule, we've got two carbon atoms, and we've got to form two bonds between them using the p orbitals. So remember that the simplest way to do that is to have p orbitals arranged like this. So you have one oriented like that, and the other oriented the same way. And as you bring those two carbons together, these two are going to overlap end over end. Okay, so you get end over end overlap, and the consequence of that is that you get an orbital that looks kind of like this, where the electron density builds up in the middle in between the nuclei, and that's a sigma bond. Okay, so basically all of the bonds, single bonds that you come across, and the first component of any multiple bond you come across is always going to be a sigma bond, because that's the most effective way for the orbitals to overlap. But if you're going to make a double bond, you need a second pair of orbitals to overlap, and if you remember that the p orbitals are at right angles, then this second pair is going to be oriented like this. Okay, and so these ones can only overlap sideways. And the effect of that sideways overlap is that you get a region of electron density up here and down here. And that combination of the two sideways overlapping regions is a pi bond. Okay, so that's how a double bond forms, that you have one sigma bond and one pi bond, and therefore the correct answer for that one was A. Question 15, we've got these four compounds, and we have to find the one that meets all three of those criteria. It's unsaturated, it's alicyclic, and it has an alkyl group. So this one is certainly unsaturated because you have this delocalized pi system in the ring, but it's not alicyclic. As soon as you have an aromatic ring like that, it's aromatic, it's not alicyclic. So that one falls there. It does have an alkyl group, because an alkyl group, remember, is just an alkane that's lost one of the hydrogens and is instead using that as a bond to link it onto something else. So it's a saturated group attached onto the rest of the molecule. So it has a methyl group there. So it meets two of the criteria, but not three. This one is alicyclic because it contains a ring which is not a benzene ring, so it's not aromatic, so it is alicyclic. It does contain an alkyl group because it's got a methyl group there, but it's not unsaturated, because unsaturated means that you have a double bond between carbon atoms, or possibly a triple bond between carbon atoms, and that one hasn't. So it's not that one. This one is unsaturated because you've got the carbon-carbon double bond. It is alicyclic because you have a ring which isn't an aromatic ring, and it has an alkyl group because it has the methyl group there. So C is going to be your answer. Let's just check why it's not D. It is unsaturated, it is alicyclic, it's got the ring there, but it doesn't have an alkyl group. Although it's got a branch, it's unsaturated, the branch, so it's not just an alkyl group. So that one fails there. So C was your answer. Question 16 is a real giveaway one if you've just learnt your basic definitions, because an electrophile, you just have to learn, is an electron pair acceptor, and there it is, that's answer A, so it's as simple as that. So in question 17 we have one of these addition polymers, formed from alkenes, and remember they always have the same basic architecture, which is that the repeat unit always has 2 carbons along the backbone and everything else just hangs off the side. So you can see that if we make this the first carbon in the repeat unit, this will be the second one, and that will be the end of it. And you can see that's indeed the case because the next carbon is the same as that one, and so on. So that's the basic repeat unit. And the relationship is that the monomer has the same structure, except that it doesn't have the linking bonds connecting it to the rest of the molecule, so that bond won't be there and that bond won't be there, and instead it will have a double bond there. So the monomer will be that. And if you translate that into a more explicit formula, we've got CH2 there, CH, CN, which is indeed answer C for that one. If you don't like working with the skeletal formulae when you're figuring out what's going on with polymers, an alternative strategy would be to straight away redraw this with a displayed formula, and you could do that. I mean, it would take a little bit of time, but you could do that. So this here, you obviously have CH, CN, and then you have here CH2. So you could say, right, yeah, there's my repeat unit, and then that again just leads you to the same answer. So whatever you're most comfortable with. Okay, so 18, you have mass spectrometry questions. Remember, what happens in a mass spectrometer is that first of all the whole molecule loses 1 electron to form a molecular ion, and then that molecular ion tends to be unstable, it's in a high energy state, and it tends to fall to bits. And what you have to look for are fragments that you can form from that molecular ion by just breaking 1 bond in the structure, because the highly populated fragment ions are likely to be formed just from breaking 1 single bond. So what you've got to do here is go through and see whether you can get a fragment with a mass that adds up to 43 just by breaking 1 single bond. So if we try that for A, there's no point worrying about the single bonds to hydrogen because they'll obviously just take 1 off the structure, off the MR, so that's not likely. So the only ones we have to worry about are this one, and this one. And we just have to work out what masses we'll get if we break each of those. So it's a good idea always to start off by working out what the MR of the whole molecule is, and then you can easily see what you're going to get left behind when you break bits off. So the M+ ion, which is the molecular ion that you get when the whole molecule is formed, has the same mass equal to the MR, which is 74 for that one. If you break OH off it, that adds up to 17, and that will give you, therefore, a fragment either of 17, or if you take 17 away from there, you get 57. So that can't give you the 43. If we break this one off, then you're either going to get C2H5+, which adds up to 29, or you're going to get COOH+, which adds up to 45. Okay, so we came close with the 45, but close isn't good enough, it's got to be 43. If you break this one, you'll get CH3+, perhaps, which could give you 15. Well, we're saying perhaps because remember, you can never guarantee you will get these ions, it's just that you could. Or you get CH2 COOH, which comes out at 59. So you can see that straight away we've hit the jackpot, because those are all the possible ions that you could get, and none of them is 43. So A is going to be the answer. So it's just worth going through and seeing how you can get 43 from the other ones, just to make the point. But in the exam you wouldn't have to do that, because you'd say, right, I've got that one, so move on. Okay, so here with this molecule, this has a total MR of 60, so the molecular ion has an M over Z equal to 60. So if we break off the OH here, that takes 17 away, and that would give you either 17 or, crucially, 43. Okay, so we've got our 43 this time, and it would come from an ion, which remember is CH3 C double bond O, and if you have to write them down, remember in mass spec they are ions and you have to show the positive charge. So CH3CO plus would account for the 43 in that case. In this one, again the MR adds up to 74. So if we break off the OH, we'd get either 17 or 57. So that's no good. If we break it here, though, we get either C3H7 plus, which is 43, or we get CH2OH plus, which is 31. And you can see we've got our 43. So it's a different ion, it's not the same as that one, but it has the same M over Z. So in this case, the 43 would come from CH3, CH, CH3. And again, put the bracket round it, put the positive charge outside. This one again has an M over Z, an M plus ion with an M over Z of 60. So if we lose 17 from that, we're going to get 43, and you can see straight away that if you just break it there, you get 17 and 43. So again, that one can, and so this time it's going to be CH3, CH2, CH2 plus, which gives us our 43. So that was just for practice, because it is important that you're confident generating those fragment ions, but in the exam question you'd have got the answer straight away by looking at A. So question 19, you've got these 4 statements about what happens when infrared radiation interacts with molecules, and you've got to decide which one is nonsense. So the first one, energy from infrared causes some covalent bonds to vibrate more. Well, you know that's true. That's the whole basis of infrared spectroscopy, where you're looking at individual bonds or groups of bonds vibrating when they absorb. The reason it says vibrate more is a bit strange, but it has to do with this curious thing called 0-point energy, which means that actually covalent bonds are always vibrating a little bit. Even at the coldest temperatures, they're never actually sitting still. But when they absorb infrared, it lifts them up into a higher energy state where they're vibrating more. B, absorption of IR by some atmospheric gases is linked to global warming. Again, you know that that's indeed the case. Infrared radiation is used to monitor gases causing air pollution. Yes, it is, because you can get peaks characteristic of individual pollutant gases, and just by measuring the intensity of that peak, you can work out how much of that pollutant there is in your air sample. And D, action of IR radiation on CFCs leads to the formation of chlorine radicals. That's the one that's wrong, because remember, infrared radiation doesn't generally have enough energy to break covalent bonds. It's UV radiation in the upper atmosphere that breaks the carbon to chlorine bond in CFCs and sets that whole pathway in motion that leads to destruction of ozone. But the initiation step is indeed formation of chlorine radicals. That's the one that's wrong, because that would be UV. Okay, so question 20, we have this infrared spectrum, and we have to decide which of those compounds could have produced it. So the important thing is to go through and identify the particular functional groups. Remember that this whole half of the spectrum you can't interpret, because although there could be some bands there like C single bond O which would be useful, actually you can't tell whether they're there or not, because you get all kinds of peaks there in the same kind of positions which come from other things. So don't ever try to base your deductions on that fingerprint region, which is basically from 1500 through to the end. So we're just focusing on this half of the spectrum. Hopefully by now you're used to the idea that you always get this cluster of sharp peaks around 3000 wave numbers, which is CH, so don't go misinterpreting those as anything else. If you see sharp peaks focused around 3000, they're CHs. So basically they're not useful, because almost all organic compounds contain CHs. So we're really talking about this peak and this peak are the interesting ones. So if you see a strong peak in between 1500 and 2000, your suspicion is going to be that it's C double bond O, because you've seen that lots of times. But remember, don't just say, yeah, that looks vaguely right. You've got to check the position matches your data sheet. So you check C double bond O on your data sheet, and it says that it should be 1630 to 1820 wave numbers. So you draw a line at 1630 and it comes there somewhere, and you draw a line at 1820 and it's there somewhere, and you say, yeah, that peak is nicely sandwiched in there. So that one fits C double bond O. This one looks like an OH, but remember, with OHs you have to distinguish between carboxylic acid OHs and alcohol OHs. Never just say it's an OH, because you've got to show that you understand that there are two different types of OH. Carboxylic acid OH is 2,500 to 3,200. It's a huge broad thing. So 2,500 is sort of there, 3,300 rather is sort of here. So what you would get if it was a carboxylic acid peak is something enormous that looks kind of like that. Okay, a massive broad peak like that, and you clearly haven't got that. So it's not a carboxylic acid OH. Alcohol OH is 3,200 to 3,600. So if we mark that on there, so 3,200 is going to be sort of here somewhere, and 3,600 is going to be here somewhere, and you can see that one fits nicely. Okay, so that one is an alcohol OH, 3,200 to 3,600 wave numbers. So that's what you've got. And so what you need is a molecule that has both of those things. And obviously the trap you've got to avoid is that a carboxylic acid would have CO and OH, but it's not a carboxylic acid. So looking at your possibilities, can't be A because that is a carboxylic acid. Could be B because that's got the carbonyl group and ketone there, and it's got the alcohol OH, so B looks like the right answer. C has the OH, but it doesn't have a carbonyl group, and D has a carbonyl group, but it doesn't have an OH, so it's got to be B. So that's the answer.